I'm Alex Chen, Provost of the CTU University. Professor Weitz is a member of the U.S. National Academy of Science, the National Academy of Engineering, and also the American Academy of Arts and Sciences. He was also elected as a Fellow of the UK Royal Society of Chemistry and the American Physical Society. Today, Professor Weitz will deliver a lecture entitled Dripping, Jetting, Drops, and Wetting, the Magic of the Microfluidics. May I now invite Professor Weitz to deliver his talk. Please join me to welcome him.
Okay, well, thank you very much. It's really an honor and a pleasure to be here. And I'm going to try and tell you something about some work that we've been doing, well, probably close to 10 years now. And I always have to say at the beginning of a talk like this that all of the work that I'm going to tell you about, none of it is my own. All of it is work of talented students, postdocs, and visitors in my lab. A lot of what I'll tell you about today, in fact, was done by Anderson Shum, who's now a professor at Hong Kong University. Other stuff, Shin Yun contributed a lot. Adam Abate, who's a professor at UCSF, and Jeremy Agresti at Biorad. Langyan Chu from Sichuan University also. And Andy Utada, who's now in Japan. I'm going to tell you something about microfluidics. So most of you probably have heard something about microfluidics, and you think that microfluidics, oh, it sounds like microelectronics. It's just the same thing as microelectronics, but for fluids, and you're right. That's what it is. And another common expression for that application is lab on a chip. It's reducing your whole lab. This is very important, I learned. It's very important in City University. It's reducing your lab, which here is very small to begin with. It's reducing it onto the size of a chip. So imagine if you did that. Imagine how many more faculty members you would have. Actually, I'm not going to talk about that till the end of the talk. I will tell you a little bit about that. That is, in fact, what we spend a lot of our time worrying about. We really think about that to a large extent. But at the same time, we've been thinking, or we've spent a lot of our time thinking about, can we make materials using microfluidics? And I would like to argue with you that, in fact, you can. Now, I want to convince you of two things. First of all, that you can make interesting materials. And secondly, that you can do it in a way that actually is commercial, that you can make it in large enough quantities. And why do I even ask something sort of stupid like that? Why would I care? Well, back when we first started this work, one of my colleagues, a really wonderful colleague, Howard Stone, who was working at the time at Harvard, and since he's moved to Princeton, he's really a fabulous, fabulous scientist. And a large personal care company came to him and said, please, Howard, can you figure out whether we can do this commercially? Because they were interested in commercialization. And the problem, as I'll show you, is that you don't make huge amounts of quantities. I'll explain all of this, why we do that. But Howard worked very hard for 3 years, and after 3 years, they decided, no, they can't. Of course, when I heard that, no, you can't do it, I said, that's the perfect problem for my students to work on. So I want to try and convince you that my students were successful, we were able to do this, and in fact, I saw yesterday in the Chinese media, in fact, I saw it on WeChat, something to confirm, and I'll show us what I mean today. So how can we make interesting materials from microfluidics? Well, it all starts from the fact that we know how to make droplets. And the nice thing about a droplet is, if you think about a droplet, it's round, it's a sphere, and it's really a perfect sphere. In fact, you have to work very, very hard to change it from spherical. And the fact that it's spherical means that you can put something inside of it, but also you can use it as a template. You can use it to build new structures around it. So I'll show you, can make very, very uniform drops. Every one is exactly the same as the next. And we'll use each one of these drops to build something else around it, to make a more complicated structure. And I'd like to show you that these complicated structures besides being very elegant, very interesting, very fascinating properties, are also functional. They actually do something that's useful. We can learn interesting new physics, but the key to all of this is that we can control the way we make things, the way we mix the fluids, by just creating relatively simple, relatively controllable, and relatively easy to use microfluidic structures to control the way we make the drops and the way we mix the fluids. So, drops. Actually, you know all about drops. If you, for example, you know, there's the British tradition still in Hong Kong, so with tea sometimes you put milk, or if you have milk, or if you make a salad dressing, milk. What's milk? Milk is white because it's got little drops of fat inside the milk. So 2% milk. Ever drink 2% milk? How many drops of fat does it have in it? 2%, right? Whole milk is 4%. Skim milk, no fat. By the way, skim milk still looks white, but not as white as the other. So the fat particles, they're fat drops, they scatter light, and the more fat there is, the more light that's scattered, the whiter the milk looks. Heavy cream is much whiter than skim milk. Okay, so imagine now making the drops. How do you make the drops? Well, milk normally is pasteurized, and it's also homogenized. Homogenized means it's really stirred very hard to make very uniform drops. Another way of making drops, so it's an emulsion. It's a mixture of two immiscible fluids, oil and water, fat and water. Another one is oil and vinegar for a vinaigrette. How do you make an emulsion? How do you make drops of one fluid inside a second fluid? So Anderson asked you that question. Here he is looking at you, Professor Shum from Hong Kong University, asked you that question. How do you take two fluids and mix them together? Anybody know? Very simple. Did I hear somebody say shake? Right? Shake them up. This is what you get. Drops, but lots of